Hi everyone, today we'll make a presentation on our research topic named as blockchain-based federated learning frameworks quantum security. This is our presentation agenda for today. I will first introduce background and our research questions. Then prior works and our innovation will be present, followed by fundamental things, which is intended to give you general ideas of our topic. After that, how we will identify the quantum vulnerabilities of some BFL frameworks. Finally, Tiancheng will present our method on improving quantum resistance of BFL. Our contributions and future directions will be summarized at the end. Okay, let us start with background and motivations. Well, federated learning is a distributed machine learning system which can help to minimize the risk of data breach in the traditional machine learning workflows. However, it will suffer many pinpoints such as single point failure and data poisoning. For building a more robust system, the state-of-the-art solution is bind federated learning with blockchain, which aims at resolving all pinpoints at one time, which this is so-called BFL. However, this is not the end of the story. As the emerging of a quantum algorithm, there is a big challenge raised on blockchain security, so as on BFL. The motivation for us is finding a way to build a quantum-safe federated learning frameworks which try to maintain the reliability in the post-quantum era. Based on the motivations, our research question is made up of two parts. The first one is to investigate how resistant of current BFL against the quantum attacks. And the other is figure out how to further improve its resistance to quantum attacks. Answering them can help to identify the root cause and the possible future direction in this area. This is a visualization of our topic related to current technology. As you can see, we focus on the intersection area of federated learning, blockchain, and quantum attacks. Currently, there are a lot of research works on either BFL or quantum attacks on blockchain. So far, none of them touch on the research field we are exploring. So the main innovation in our works is to propose a feasible solution for BFL against the quantum attacks. Okay, let me introduce some fundamental things about BFL. Blockchain is perfectly suitable to integrate with federated learning as it can resolve many issues at one time. First, blockchain is a peer-to-peer network. This decentralization can help to tackle single point failure issues because there is no need of central servers. The blockchain consensus will establish a standard verification process which can help to eliminate pointing data. Last but not least, the incentive layer inside blockchain can provide financial rewards based on the contribution of system participants. This gives more motivation for clients' engagement. So there are some reasons why BFL is popular imitation for machine learning systems. Now, let us look at the BFL workflows. First, clients need to fetch the current global models from blockchain network. After that, they will train their model based on the local dataset to generate individual updates. These updates are uploaded to miners for validation according to some consensus, and only the verified submission will be further forward to distributed ledgers for global integration and storage. Finally, the reward or punishment will distribute to clients based on their local update clearness. There are two sets of everything. We can find that the current BFL reliability highly dependent on the blockchain itself, so that any thread on blockchain is also concerned with BFL. The quantum attack will be one of them. This is because hash function and digital signature, they form the security foundation of the blockchain, but they are both vulnerable to quantum algorithms such as shorts and groovers. Next, how we will introduce more details about the quantum attacks on BFL frameworks.
Thanks, Xiaoyu. Now we will move on to the overview of the BFL framework's quantum vulnerability. We classify different types of BFL frameworks as permissioned BFL frameworks, which consist of private and consortium BFL frameworks, and permissionless frameworks, which consist of only public BFL frameworks. Here, the classification standard is based on the classification on blockchain. The public BFL framework is a BFL framework that allows everyone to participate in the learning process without any further certification. It is fully decentralized and it has a high level of transparency, which makes it highly immutable. So the framework has better performance than the permissioned ones. The number of participating nodes is large and the single point of failure issue can be solved naturally. However, the public key cryptography used to secure transactions is vulnerable to shorts attack, and the attacks can forge transactions easily. Permissioned BFL allows only part of the users to participate in the learning process, or it is totally controlled by the central authority. Similarly, it had the same issue as public BFL, and the performance is even more poor due to its low level of mutability. All types of BFLs use hash functions which can be broken by Gruber's attack, and different BFLs might use different consensus mechanisms which have different resistance to quantum attacks. We then present 3 different featured BFLs, and we analyzed their performance on the quantum attacks. We have found that the frameworks that use public blockchain has better resistance, and the reason has been mentioned before. And we found that the proof of stake consensus mechanism is the most vulnerable compared to proof of work, delegated Byzantine fault tolerance, and practice BFT, because it requires the staker to participate in the staking transaction in the set creation phase, and this can be attacked by Shor's algorithm. And some consensus mechanisms like DBFT has a built-in finality, which means that they are extremely hard to roll back once the consensus is built. So the consensus with this feature should perform better than the others to quantum attacks. The hash function used for the digital signature or verifying updates is believed to be secured for now, as the Gruber's attack is not as harmful as Shor's. It does not improve the speed of breaking the scheme that much, and the digital signatures like the ECDSA that rely on the difficulty of solving the discrete logarithm problem are extremely vulnerable to Shor's attack. Now we'll move on to the Tiancheng's part.
Thank you, Haodi. In the remaining part of the presentation, I'll first introduce the quantum-safe technologies for BFL frameworks. Then I will conclude our contribution and point out future research directions before wrapping up the presentation. Let's start with quantum-safe technologies. BFL frameworks should consider replacing quantum-vulnerable classical crypto systems with quantum-safe technologies such as post-quantum crypto systems and quantum-based technologies. Post-quantum crypto systems include quantum-safe public key algorithms and hash functions. BFL frameworks need to increase hash length to resist collision detection by quantum algorithms. The security basis of quantum-safe public key algorithms should be quantum hard problems such as coding theory problems, multivariate systems, and lattice problems. While multivariate-based algorithms underperform, lattice-based and code-based algorithms demonstrate comparable performance. After 6 years of evaluation and selection, National Institute of Standards and Technology announced the standardization process of 4 state-of-the-art post-quantum algorithms in July. 3 final winners are from the lattice-based family, while the remaining is hash-based. BFL frameworks should consider using Crystal's Kyber for encryption because it's a clear winner. For digital signatures, Crystal's dilithium is preferred in general cases because of its low total cost. When bandwidth is limited, Falcon has an advantage in transmission cost. In case the lattice problems are broken, BFL frameworks should have the hash-based 6+ as a backup. Quantum technologies have also offered quantum security opportunities for BFL frameworks at different levels. At a lower level, BFL frameworks can use foundational quantum technologies such as quantum key distribution, quantum random number generation, and quantum digital signatures to replace their classical counterparts. Despite limited bandwidth and availability, those technologies can achieve unconditional security due to their unbreakable physical security basis. At a higher level, BFL frameworks can also use established quantum secure blockchain mechanisms, such as quantum voting, to achieve quantum security. Now that I've introduced quantum-safe technologies, next I will summarize our contribution and future research directions. Our main contribution is analyzing the quantum vulnerabilities in BFL frameworks and proposing quantum-safe technologies for BFL frameworks. We classify BFL frameworks and analyze representative frameworks' quantum resistance. We also highlight its standard post-quantum algorithms and other quantum-based technologies for BFL frameworks. After the research, we found the following research directions. First, implementation and optimization of post-quantum crypto systems in BFL frameworks. Second, theoretical design proof of concept experiment of quantum-based BFL frameworks. Finally, balancing the quantum security level and the cost in BFL frameworks. Our research aims to investigate the quantum vulnerabilities in BFL frameworks and propose potential improvements. Readers of our report can get up-to-date information and promising research directions in this field. That's all. Thank you.